Let's apply the law of conservation of momentum in two directions. So in two dimensions, I guess. So let's start with a ball that's moving this way at 4 meters per second, and it has a mass of 0.5 kilograms. Now, I'm going to dash in this line that shows its initial velocity. But what happens is I'm going to put a second ball right here. And this ball is also 0.5 kilograms, but it's at rest. And so they collide right here, and as a result of that, the green ball is going to move this way at an angle of 30 degrees below the initial direction, and the blue ball is going to move this way at an angle of 30 degrees above the initial direction. And so my question is, how fast is each one of these balls moving? Now, in order to solve this problem, we're going to use the law of conservation of momentum. But the law of conservation of momentum, we use it just like we use projectile motion. We treat x and y independent. So in x, the initial momentum in x is 4 times 0.5. The final momentum in x, I'm going to go ahead and draw in some components. I have the velocity, let's call it the blue one A. I have velocity A in y, and I have velocity A in x, and then I of course have velocity A. And then down here in green, I have the velocity of B, we'll call it, and then there's the velocity of B in y, and the velocity of B in x. Now, we have to be careful when we measure angles, or we have to be careful with sign, but we'll get there. So 0.4 or 4 times 0.5, that's the initial momentum in x, equals, and now I have to take mass. So each one of these masses is 0.5, and so I have the mass of 0.5 times, and I only want x, so I'm going to say VAX, plus 0.5 times VBX. Right? So there's the total momentum in x. Now, I don't really like using x and y as I have these angles here. We'll come back to that. Momentum in y is 0 to start with because this thing wasn't moving in the y direction. It was moving only in the x direction. Equals, and then down here I have two things again. I will have 0.5 times VAY plus 0.5 times VA or VB y. So again, I'm keeping my x's and y's separate. Now up here, I can make some substitutions, right? VAX is really VA times the cosine of 30. So 4 times 0.5, I guess I could have written that as 2, is 0.5. VAX is VA times the cosine of 30 plus 0.5 VBX. VBX is, of course, this angle here, and this is also cosine 30. So plus VB cosine 30. And the cosine of 30 is the square root of 3 over 2. So this becomes 2 equals half of square root of 3 over 2 VA plus half of square root of 3 over 2 VB, and so 2 equals square root of 3 over 4 VA plus square root of 3 over 4 VB. However, let's come down here. We have VAY plus VBY. Well, we're going to replace that with VA and VB. So 0.5 VAY. VAY is VA sine 30. VA sine 30 plus 0.5 VBY, which is VB. Now I need to be careful with this. I'm actually measuring here, and I'm down in the second quadrant. So this is actually sine of negative 30 degrees. So I do have to be careful with that. And then if I work that out, this is, of course, half of half, because the sine of 30 is a half VA, plus 0.5 VB times the sine of negative 30, which is half of negative half VB. And so I get 1/4 VA is equal to, because I'm going to add that half over, 1/4 VB, and what I see is VA equals VB, the quarter goes away. And so up here I have 2 equals 3 over 4 times VA plus VA. right? Because I make that substitution, and this is square root of 3, sorry. And so now I have VA plus VA, sorry. And so now I have 2 equals the square root of 3 over 4 times 2VA. That 2 is going to make that back to a half. And so now I have 2 equals square root of 3 over 2 times VA. And then I'll go ahead and multiply by 2 over the square root of 3 and get 4 over the square root of 3 equals VA. Once I know VA, I also know VB. They have equal magnitudes, and they are, of course, in different directions.